If an AI makes a mistake while writing Python code, you get a syntax error. But if an AI makes a mistake while driving a robotic chassis, it, drives straight through a glass table.
Yeah, the physics of the real world are entirely unforgiving.
Exactly. And latency is literally deadly. Welcome to AI Paper Slap. Today, we're pulling the pure signal directly from a paper titled Hy-Embodied-VLM-1.0 Efficient Physical World Agents, fresh from the Tencent Robotics X-High Vision team.
It is a fantastic paper.
Right, so let's get straight to the core insights for you listening. This paper introduces a highly efficient vision language model that's purpose-built for physical world agents.
Using a mixture of experts architecture.
Yes, and MOE architecture that activates only 3 billion parameters per token during inference, but it still hits performance metrics comparable to their previous 32 billion parameter model.
Which is a huge leap in efficiency.
It really is. But the real breakthrough here is their action-centric training pipeline. They lean heavily into group relative policy optimization, or a GRPO, along with deterministic task-aware rewards, and this novel rejection sampling fine-tuning method.
Right, and that pipeline explicitly teaches the model how to reason, how to act, and critically, how to recover from physical failures.
Exactly. So if you're building agents that actually need to interact with the real world, this paper is providing you with a literal blueprint for training small, highly capable models.
Because, the underlying problem this blueprint solves is that fundamental difference between perception and physical causality.
Right. Standard vision language models, even the massive frontier models, they just fail catastrophically in robotics.
Yeah, they do. A standard model can process an image and tell you with really high accuracy that a ceramic mug is sitting on a wooden table. But actually taking action requires an entirely different cognitive mechanism.
Because it's not just labeling anymore.
Exactly. You need a model that inherently understands how its own physical interventions will, alter the state of that environment over time. You're dealing with friction, gravity, momentum, all of it.
Which means we need to train for something far beyond basic image captioning.
Right.
And the paper tackles this by defining a 3-tiered action-centric capability taxonomy. They structure both the training data and the final evaluations around these progressive dimensions.
Yeah, so the first tier is action-relevant state understanding.
Right, so understanding the exact geometry of the mug's handle. That's step 1.
Exactly. But just knowing where to grab doesn't mean the robot knows how to move its arm without knocking the mug over.
Right, so how does the model bridge that gap between static perception and actual physical physics?
Well, by moving to the second tier, which is action transition reasoning, this is all about local causal transitions.
Okay.
The model needs to evaluate the spatial preconditions. Before it even moves, it has to compute, is there a clear path to the mug? What is the center of mass?
And then it predicts the execution.
Yeah. And crucially, it calculates the post-conditions. If a robot attempts to pour water from a pitcher, it isn't just executing a spatial rotation.
Right. The water moves.
Exactly. It has to understand that tilting the pitcher shifts the liquid's center of gravity, which dynamically changes the required torque on the robotic arm's joints.
Wow.
Yeah, it must predict that immediate physical state change induced by its interaction.
I always think of standard digital agents as basically brains in a jar playing chess. They have this perfect static view of the digital board, and the pieces only move when they say so.
Right, it's totally isolated.
But embodied agents are brains in a body that occasionally drops the chess piece. The environment is noisy and, motors slip. They have to know how to pick the piece back up.
Which brings us directly to their third tier, which is sequential and adaptive reasoning.
So how do you actually train an AI to detect its own failure? How does it know it dropped the piece and needs to recover?
Well, you have to explicitly design the dataset around failure. Standard pipelines often train almost exclusively on successful, perfect, expert demonstrations.
Right, just perfectly executed tasks.
Exactly. And if a model only ever sees perfection, a single misstep puts it in an out-of-distribution state, and it just freezes or gets stuck in a loop.
Oh, that makes sense.
Yeah, so Tencent curated this massive data set of egocentric and robotic manipulation videos, but they went in and explicitly labeled the preconditions, the effects, and the interstep dependencies.
And they added the failure states, too.
Right. They integrated what they call failure-aware robotic reasoning data.
So they're intentionally injecting chaos. They feed the model perturbed plans and, edge case failures.
Yeah, they feed it sequences where the robotic execution goes completely wrong or where the initial task plan is fundamentally flawed given the environment.
What does the model have to do with that data?
In training, it's forced to judge the execution status from the visual frames, identify the specific erroneous action, and then generate textual recovery-oriented suggestions.
Give me an example of that.
So, if it tries to place a book on a shelf, but the book slips and lands flat on a table, the model learns it can't just rerun the pickup subroutine.
Because the book is flat now, not vertical.
Exactly. It must recognize the state changed from vertical to horizontal, recalculate the required gripper angle, and synthesize an entirely new corrective behavior.
It essentially learns that failure isn't an endpoint. It's just another physical state it needs to transition out of.
Beautifully put. Yeah.
But processing all of this complex causal data, analyzing high-resolution video frames, running long chain-of-thought reasoning, checking preconditions that usually requires massive, dense models.
It does.
And in real-time robotics, latency is the ultimate bottleneck. If your model takes 2 seconds to process the physics of a slipping book, well, the book has already hit the floor.
Right, exactly.
So the inference cost has to remain incredibly low. Looking at the architecture here, they're using the Hy-3A3B language backbone and the Hy-VAT2 vision encoder.
Yeah, and the critical design choice, keeping that latency down, is the mixture of experts or MOE architecture.
Because a dense model is just too slow?
Right. In a traditional dense model, every single parameter in the network is activated for every single forward pass. If you have a 30 billion parameter model, you're pushing data through all 30 billion weights just to decide whether to move an inch to the left.
Which creates a huge computational bottleneck.
Exactly. But with the MOE setup, the network features a gating mechanism that dynamically routes each token to a small, specialized subset of expert neural networks.
This means it operates with a much larger total parameter count for capacity, but it only activates about 3 billion parameters per token during inference.
Right.
So for the machine learning engineers listening who might be used to dense models, why is MOE the specific key to balancing this high reasoning capacity with the low inference cost required for physical hardware?
Well, embodied AI is inherently heterogeneous in its processing demands. You're asking the network to do vastly different types of math depending on the millisecond.
How do you mean?
So sometimes it's doing heavy 3D spatial geometry to map a room, and other times it's just parsing a high-level semantic instruction like, find the kitchen.
Oh, I see.
Think of MOE like the division between deep thought and muscle memory in humans. You don't use your advanced calculus skills to catch a falling cup.
Right, you use highly localized, fast muscle memory.
Exactly. The MOE gating network routes the computation only to the specific experts relevant to the immediate physical task. It provides a massive reservoir of specialized causal knowledge.
But without the lag.
Right, because you aren't paying the computational tax for the whole network on every token, the latency stays low enough for a robotic chassis to run it inside a real-time control loop.
Okay, so we have the MOE architecture routing efficiently, and we have the failure-aware data from supervised fine-tuning. But looking at the paper, the most highly technical part of this entire pipeline is how they optimize the model post-SFT.
Using reinforcement learning.
Yes, using group relative policy optimization, or GRPO. Now, we've seen GRPO heavily utilized recently in pure reasoning and math models, but applying it to multimodal embodied agents acting in 3D space is a completely different beast.
It really is.
I noticed they completely skipped building a value network here.
They did, yeah, and it is a massive efficiency gain because in standard proximal policy optimization, or PPO, you have to train two separate networks.
The policy and the value networks.
Right. The policy network decides the actions, and the value network estimates how good a particular state is just to establish a baseline.
And doing that for video is rough.
Oh, training a separate value network alongside a policy network for high resolution, multimodal video data is incredibly memory intensive. It often just maxes out GPU clusters.
So GRPO sidesteps this entirely.
Exactly. It estimates the advantages directly from a sampled group of responses.
Okay, so for given multimodal input, let's say, a video frame of a kitchen and a query to open the fridge, the model samples a group of 16 different reasoning and action trajectories from its current behavioral policy. Right. It scores each of those 16 responses, averages them to create its own relative baseline, and then updates the policy using a token-level clipped surrogate objective.
Yes.
But I noticed they used a really unusual clipping range when setting up this pipeline. It wasn't symmetric. They set an asymmetric clipping range of 0.8 to 1.35. Why skew the upper bound like that?
So that asymmetric clipping range is fundamental for stabilizing long-chain multimodal RL. Standard PPO often uses symmetric clipping, typically 0.8 to 1.2.
Just to prevent the policy from updating too drastically in any single step, right?
Right. But in long-horizon reasoning, your model will occasionally sample a rare token that represents a massive breakthrough in the causal reasoning chain.
Like a true aha moment for solving the physics problem.
Exactly. The asymmetric upper bound of 1.35 says, hey, this trajectory is highly advantageous. Aggressively rewrite your behavior policy to favor this path.
But the 0.8 lower bound still acts as a strict guardrail.
Yes. If the model samples a terrible trajectory that leads to a robotic collision, the 0.8 bound penalizes it without completely destroying the underlying baseline knowledge.
That's smart. And there's another neat trick here, too. If a sampled group of 16 responses has 0 reward variance, meaning they all scored exactly the same, either all perfectly or all terribly, they mask that entire group and drop it from the gradient update.
Yeah, because if every sample scores the same, there's no relative advantage to learn from. It's just mathematical noise at that point.
Right. But that actually brings up the absolute hardest part of reinforcement learning for physical robotics, which is the reward function.
Oh, absolutely.
How do you accurately, programmatically score a physical action? If the model outputs a complex 6 degree of freedom trajectory for a robot arm, how does the RL pipeline actually know if it's correct?
Well, Tencent implemented a dual reward system, but their primary guiding principle is to use deterministic, structure-aware rewards whenever humanly possible.
Deterministic rewards.
Okay. Yeah. So if a task requires predicting a bounding box around an object, they use a continuous intersection over union, or IOU, reward to calculate the exact pixel overlap.
Makes sense.
And if the task is a spatial direction question, they extract the model's final committed direction and score it using a strict hit and no contradiction rule.
Okay, so it gets a reward of 1 if the predicted direction geometrically intersects with the target reference and doesn't contain any axis opposite directions. Otherwise, it gets a 0.
Exactly.
But hold on, writing deterministic, hard-coded math rules for every possible spatial interaction sounds incredibly brittle. I mean, we've spent the last 2 years in machine learning moving entirely away from hard-coded rules toward highly capable LLMs acting as judges.
We have, yeah.
So why take a massive step backward here and rely on rigid geometry? Why not just pass the trajectory output to a frontier model and ask, hey, did it grasp the mug correctly?
It comes entirely down to RL stability and gradient protection. The paper explicitly investigated this, and they found that aligning the reward structure strictly to the output format stabilizes the RL process across all these heterogeneous embodied capabilities.
Because LLM judges can be flaky.
Right. LLM judges, even the absolute best ones, they're prone to subtle hallucinations, formatting biases, and unpredictable inconsistencies.
And in RL, that's fatal.
Exactly. When you're executing token-level policy updates via GRPO, a noisy or hallucinated reward will completely destroy your gradients.
So deterministic math is just an absolute safeguard for the gradients. It just doesn't hallucinate.
Precisely. However, they aren't ignoring LLMs completely.
Oh, they do use them.
Yeah, they use an LLM judge as a fallback for they built in a critical failsafe. If the LLM judge service times out, or if it fails to return a cleanly formatted verdict, the system emits a sentinel reward and completely masks that sample from the gradient update.
Oh, wow.
Yeah. This guarantees that API infrastructure noise or a confused LLM judge never corrupts the underlying learning process of the physical agent.
They are ruthlessly filtering out bad gradients. I love that. But even with perfectly stable gradients, reinforcement learning is an incredibly computationally expensive way to scale reasoning.
Very expensive.
Generating 16 long-horizon rollouts per prompt, evaluating deterministic math, calling LLM fallback judges, it takes massive compute. How does Tencent solve the scaling problem to push this 3 billion parameter model to state-of-the-art performance without burning endless GPU hours?
They solve it by splitting the RL pipeline into 2 distinct stages and engineering a very specific bridge between them.
Okay, break that down for us.
So stage I is reasoning elicitation RL. This is where they use the GRPO setup we just talked about to teach the model how to construct deep chains of thought regarding physics and actions.
But you can't just scale that indefinitely.
No, scaling that exact process is way too expensive. So before moving to stage 2, which is the reward specialized RL, they introduce a rejection sampling fine-tuning phase.
So the rejection sampling phase acts as the bridge.
Yes. They essentially take that stage IRL policy and use it as an offline synthetic data generator.
So they dump a massive pool of physical queries into it, and for each query, they draw a small number of candidate reasoning trajectories. Specifically, it's a best of n rollout, where n equals 4.
Exactly.
But what are the filtering criteria to ensure those 4 trajectories aren't just slop?
Well, they filter the candidates based on 3 really rigorous criteria to build a pristine data set.
Okay, what's the first one?
First is answer correctness. The final predicted physical action must pass that exact same verifiable deterministic reward threshold we talked about earlier.
So it has to physically work.
Right. Second is thinking quality. Even if the final answer is technically correct, the entire reasoning trace is scored by an LLM critic to check for logical coherence, lack of repetition, and visual grounding.
Let's pause on visual grounding. That means the model can't just hallucinate a logical reason to move its arm, right?
Exactly. It must point to a specific pixel cluster or spatial reference in the image and essentially say, I am moving the arm left because this edge of the table is closer than the chair.
So if it got the right answer but used shortcut logic, it gets rejected.
Yeah, it's out. And the third criterion is self-consistency. They look for queries where the retained trajectories actually agree on the final physical answer across the n samples.
Why does that matter?
Because in a physical context, inter-sample agreement acts as a proxy to ensure the model has reliable, repeatable reasoning for that specific environment. It ensures it didn't just stumble into the correct arm trajectory by pure chance.
That makes total sense. So they take this highly filtered, pristine data set of long chain of thought reasoning, and then, and this is the fascinating architectural choice to me, they don't just continue fine-tuning the stage IRL model.
No, they don't.
They consolidate the synthetic data back into a fresh model, starting all the way back from the clean pre-training checkpoint.
That's right.
Why throw away the active RL weights and go all the way back to the pre-training checkpoint?
To prevent policy collapse and over-optimization.
How so?
Well, think of reinforcement learning, like training a dog to fetch a newspaper. If you continuously optimize and reward the dog purely for speed, it might start tearing the newspaper to shreds just to get back to you faster.
Right. It games the metric.
Exactly. The policy collapses into a narrow local minimum where it forgets its broader capabilities.
Mm-hmm.
By taking the heavily filtered, synthesized reasoning data and fine-tuning a fresh pre-trained checkpoint, they gently layer in the specific knowledge of how to carefully carry the paper.
Or in this case, execute advanced causal reasoning.
Right, while maintaining the broad, general visual and semantic knowledge of the base model. This consolidated model then serves as an incredibly stable foundation for the final Stage 2 RL, which specializes the rewards.
Man, it is a remarkably elegant training pipeline. You avoid policy collapse, you protect your gradients with deterministic math, and you keep latency low with MOE routing.
It's extremely well engineered.
So after the action-centric taxonomy, the failure-aware data, and the two-stage RL bridge, how does a 3B active parameter model actually perform in the wild against much larger networks?
The benchmark results are highly impressive. They evaluated Hy-Embodied-VLM-1.0 across a massive 38 benchmark suite. And when tested against similarly sized models, it ranks first in 19 out of the 38 benchmark.
And we're talking about strong state-of-the-art competitors in the embodied space here. It goes head-to-head against Qwen 3.6 A3B, NVIDIA's Cosmos 3 Nano 8B, and Embodied R1.5 8B.
Yeah, and it outperforms the strongest of those competitors, Qwen 3.6 A3B, by 4.4% on average across all capability categories.
That's substantial.
But the metric that truly validates the efficiency of this pipeline is the generational leap. Compared to Tencent's own previous generation model, the Hy-Embodied 0.5 MoT2B, the average performance is up 8.4%.
Wow.
And despite only activating 3 billion parameters per token, it achieves overall physical reasoning performance remarkably close to their older, massive architecture that required 32 billion activated parameters.
That is essentially an order of magnitude reduction in inference cost for the exact same level of physical intelligence. Let's ground those benchmark acronyms in physical reality for the listener real quick. They tested this heavily on vision language navigation tasks, specifically R2RCE and MP3D. What do those benchmarks actually require a robot to do?
Right, so R2RCE stands for Room-Karun Continuous Environment. It's an instruction-following task where the agent must navigate purely from egocentric vision without any top-down map.
No map at all.
None, and it hit a 57.9% success rate there.
That's wild. And MP3D?
MP3D is even harder. It's zero-shot object goal navigation. You basically drop an agent into a complex 3D environment it has never seen before with no map and tell it to find a specific object.
And that would do.
Hitting 38.3% on MP3D proves the model isn't just memorizing routes or gaming static metrics. It actively maintains spatial memory, it maps unseen preconditions, and it executes sequential decisions in simulated physical space.
Which leaves you with a critical engineering shift to ponder. Given that this highly effective embodied intelligence relies on an MOE architecture with just 3 billion active parameters fueled by specialized synthetic reasoning data and self-correction RL, it strongly suggests that the bottleneck for physical AI is no longer raw model size. The bottleneck is high-quality causal data and latency. If models this incredibly small can effectively map complex spatial preconditions and autonomously recover from their own physical failures, does the race for embodied AI now shift away from massive server farms and entirely into optimizing inference chips natively on the robotic chassis itself?